Okay, so let's begin. Welcome to the last lecture. It's going to be a different lecture, less technical and more an overview of what we like, what's pseudo-randomness in 2024. Like how does it look like? Hopefully next time I'll give it not because it will be late, but just because thing happens, it will be a different overview. But let's see. Also bought some sugar if you want to. Let's do it in the break. I'm actually curious about one of those. It's new, so I'm going to try it. Yeah, so anyhow, right, so last lecture. So what I want to talk about today is, first of all, I want to continue the discussions on extractors. I mean, we really barely just started it. We talked about what's an extractor. We define mean entropy and we define statistical distance, and we immediately jumped to mergers without actually talking about extractors themselves. So I want to tell you what's known and at a high level, how do you construct seeded extractors? Here there was not so much of a drama as in the next story. Here, already from the first paper, people did a great job at constructing those. And there are still open questions, really interesting open problems here, but you know, it started in the 90s and ended like 10 years after, essentially. People understood this very well. Two-source extractors, on the other hand, which I'll talk about, is a different story. They were defined before seed extractors, and only I want to say recently because for me it was a present, like it was while I was there, but it's actually almost a decade ago now, so I'm feeling quite old. But like 8 years ago, maybe. Yeah, it started like 12 years ago. There was some progress, and it kind of accumulated to a very cool result that I'll talk about. Yeah, wow, 9 years ago, but it's new. For me, it's new. So anyhow, this was a very difficult problem, and we'll talk about that. Right, this was defined like maybe 10 years before that, and resolved a long time after. But now we know, essentially the state of affairs now is that we know to construct these as well as we know how to construct this. It's kind of crazy. I learned a lot from it. Like, okay, well, we'll talk about it. And so that's one thing I want to talk about. It's probably going to take almost an hour. Then the second thing I want to talk about, any by any chance someone has like a black expo thingy or something? No, okay, we'll steal from another class in back. So I move to blue because the blue is good. So the next thing I want to talk about, so this is like definitely a breakthrough. What happened here? Comparable with SL equals L and stuff like that. The other thing I want to talk about is space-bounded randomization. I want to tell you what's going on today. Say randomization. And so here, it's not like a breakthrough per se, but there is a steady and promising progress. And I think we're all quite optimistic that something very interesting will happen here soon. Like in the last 5 years, a lot of interesting things happened, but there wasn't like we improved Nissan or something like that. It was around that. So I want to talk about that and tell you how research looks today at this field. And then I want to kind of add my next course, which is about Ramanujan graphs. So I want to tell you a little bit, just in maybe like 5 minutes, about analytic ways. I'll say what analytic is when, what do I mean by that? To construct expanders, Ramanujan graphs really, essentially. Kind of a bipartite version of those, but we'll see. So this started with, I mean, there are some like precursor ideas before, but this started in works of Marcus, Spillman, and Srivastava, sequence of works in which they actually used entirely different proof strategies and techniques than before. So less algebraic, definitely less combinatorial, more analytic. Like you see an integral, there are stuff like that. everything is infinite. And to construct expanders. And what I like about this result, besides of the fact that it's like a breakthrough by itself, which we'll talk about, is that the techniques are completely different. So it's like a whole new world that's open for doing pseudo-randomness. And we're actually using those now to do other things than just constructing expanders. And then I can't help it. I'm going to have to talk about, so it's like a breakthrough that happened 55 years ago or something, started like this one, and that's AG codes, algebraic geometry codes. So the idea underlying, so the math underlying AG codes is like, honest to God, the most beautiful mathematics in existence. Like, there's nothing to do with my taste even. Just so there was. Oh, I'll talk about that. But the point is that there was this person that knew the underlying mathematics. That's what he did. It's called Gopa. I mean, last name it's Vladimir Gopa, and he just noticed, well, Reed Solomon is just a simple case of like a algebraic geometry code. So let's construct codes from algebraic curves in general. And so it took some time until people kind of really found the right way of doing that. That was like maybe 20 years afterwards. But now we know how to construct them, and like the codes here like outperform the probabilistic method. They use insane mathematics. So it's really a beautiful thing. And the reason I'm presenting it here is because I think, I mean, there are applications of that to pseudo-randomness, but I think there should be much more. So that I'm giving because of that. So actually, I said that this is an ad, but both of them are ads. So that I'm giving next semester. Of course, you are coming, and this is next year, like in a year from now, semester B. Okay. So let's start. So let me tell you a few words about seeded extractors and reminding them. Oh, wait, one more thing. Sorry. So Richard Feynman has this thing. So I'm no Richard Feynman. He had this thing that I really like, in which the last lecture in his courses were always like, ask me anything. So it didn't come with a plan, just people asking whatever they want. And I mean, he was able to back it up because he is Richard Feynman. He can answer whatever you want. I'm not Feynman, but I will try to, I mean, and this is a smaller field than physics, so I can maybe do it. But we'll spend some time actually, talking about pseudo-randomness, ask me any question, and I'll try to tell you what's known, what's not known, what can I say about it. So hopefully this will be like two and a bit, 2 perception hours, and then we'll have some time to have some fun. And okay, we'll see. And if you don't know the answer, I'm just going to lie to make up an answer. Okay.